Hi there, my name is Charles Msipa. Welcome to another presentation on complex functions. In this case, we are discussing how to determine power series of a given function under given conditions. So this is a follow-up of the first introductory lecture on power series of complex functions. And this discussion will be a kind of explaining examples of different conditions under which you can develop power series expansion. So let's start this way. We're given an exercise here which says find the power series in form indicated below, representing the function f of z is equal to 1 over z minus 2. The first condition, we are required to develop a power series of function of this form. In other words, under the condition that the absolute value of z is less than 2, meaning that we want the power series expansion of this function within the disk or the circle centered at the origin. Then let's start with the first part where we're given this. Now we have the function given as f of z equals to 1 over z minus 2. Now we need to develop this, expand this function in power series of this form. So now our initial step, let me number is 0, is the condition z, absolute value of z less than 2. First of all, we must understand that this is equivalent to absolute value of z over 2, which you can take as absolute value of z over 2 is less than 1. So now if we take this as a kind of a sum of a geometric series, in this case we're going to expand this applying the geometric series, we would know that the ratio for the geometric series to converge, the absolute value of the ratio must be less than 1. So then, if that is the case, this series would be of this nature, where it's got a0 plus a1 r plus, sorry, a0 times r plus a0 times r squared plus dash dash a0 times r to the power k, and it continues to infinity. Now if this geometric series was convergent, then we know that the sum would be a0 over 1 minus r. So what you should note here is that this is a power series in terms of r, and when it's convergent, this is its sum. So what we can try to do now is try to manipulate this expression in such a way that we come up with an expression which is similar to this, and now it's expressing this as a sum of a geometric series. In this case, we would say in this case here, this is convergent when the absolute value of r is equals to, sorry, is less than 1, So in this case, we can parallel z over 2 and r. Now as we take our z over 2 to represent r, then it means then we should, in our first step now, after understanding this condition, we'll take the expression of f of z and then manipulate it in such a way that it looks like some kind of sum of a geometric series. In this case, where our r is going to be z over 2. Now, if we need this expression as our r, then we need to manipulate the expression this way. 1 over z minus 2 is equals to 1 over z over 2 minus 1. In brackets, having a common factor there 2, and you must check that this is reversible to this expression. Now, when we've got this, we can see that we're closer to getting something like this, but our r is not in the corresponding position as in our geometric series. So manipulating this in that direction, we can have r 1 over, take in the denominator here, taking common factor minus 1, we're going to have minus 2 brackets 1 minus z over 2 close bracket. Now, at this stage, I think we can see that we're closer to having something like this, or we can also almost have something like this. What you can do here, we can now have minus 1 over 2, and in brackets have 1 over 1 minus z over 2. It is important at this point that in brackets, within the brackets here, this process we've carried out here has taken us to an expression which is exactly of the same form as the sum of a geometric series where a0 is equal to 1 and our r is z over 2, and satisfies the condition given here. So now if this is a sum of geometric series, now expanding this in powers of z, like the geometric series expanded in powers of r, we can now write this as follows: minus 1 over 2. What we have here is, as an expansion, is the initial term a0 times r to the power 0 plus the initial term a0 times r to the power 1 plus initial term times r to the power 2, and so on. So expanding this, our initial term is 1, so we write 1, and we know that when we multiply 1 by any number, r1 is identity for multiplication. So now what we're going to have here is going to be 1 times r, and the r in this case comes as z over 2. Then we might write here z over 2 plus 1, which is our a0, times z over 2 to the power 2 plus 1 times z over 2 to the power 3 plus dash dash, and then you can close the brackets there. Now I hope you can see that this sum, what you can call the sum of a geometric series in terms of r, which is z over 2, is developed this way. Now we can incorporate this half, which came as a result of this manipulation here, and we've got our power series as follows. We're going to have minus half minus z over 2 squared minus z squared over 2 to the power 3 minus z cubed over 2 to the power 4, and so on. In this case, you can write the condition absolute value of z less than 2. And this means that this series we've obtained here converges within the circle of radius 2 centered at the origin, and that we can present geometrically as follows. We have a circle here centered at the origin there, and we can mark this as 2i minus 2i and minus 2. So given that this series converge at absolute value of z less than 2, then mark the inside of this circle as what we would call the region of convergence for the power series which we have developed. I hope that is clear as an example. So maybe before we pass over, let's just quickly go over summarize what we've done here. So what we were given is the function f of z over equals 1 over z minus 2, and wanted to develop this as a power series, not necessarily as a power series of r, but as a power series of z. But given the condition here, we're to analyze the condition, and so that this condition was equivalent to absolute value of z over 2 less than 1. And then from there, we could relate this to a geometric series in such a way that we could be able to transform this expression to kind of a sum of a geometric series. Then after that, follow this expansion, that if you've got a sum like this, we can write, you can expand it as a geometric series this way. So what we did here, we took out the common factor first of all, 2, and we had this. After that, we saw that this position of z, in terms of which we want to develop the power series, was not the one which is favorable to us, and we don't have a minus sign before it here like r has here. So what we did, we took out the common factor minus 1 to obtain an expression like this. Now, grouping this conveniently, we had minus 1 over 2 here, and what we have here is having exactly the form of the sum of a geometric series a0 over 1 minus r, where in this case our a0 is 1 and our r is z over 0. Then we simply expand the inside square brackets as is given there in the geometric series. Then we have got our required power series satisfying the given conditions. That is the first example. Having done this manipulation to get the power series, we should not lose sight of the geometric representation of the region of convergence given by this condition, which in this case is given this way. the region of convergence is given as the inside of the circle of radius 1 centered at the origin, which is expressed by the condition. Now, this marks the end of example 1. Let's look at the next condition of the same function. The next condition requires that we develop the power series of the same function f of z equals to 1 over z minus 2, under the condition that this series is convergent within the circle of radius 1 centered at 1, because our center of a point of the series is 1. Now, what do we do now? What we need, if we're going to use the same approach of the geometric series, what we're going to do is again to try to shape this or modify this to look like a geometric series whose ratio in this case is going to be z minus 1 being in absolute and absolute value less than 1. So now what do we do now? We creatively see how we can create this ratio in this expression. So what we can do, suggest here, is to write this expression as 1 over z minus 1 in brackets minus 1. I hope you can all see that this is z minus 2. And then in the next step we can, as you know, our sum of geometric series is always a0 over 1 minus r. So now, since in terms of this series, our r or common ratio must be z minus 1. So we need to modify this in such a way that it looks exactly like this. And the only way we can do that here is to take a common factor minus 1 in the denominator and then have the denominator transform to 1 minus brackets z minus 1, and then we can write our minus 1 outside the brackets, which you can write nicely as minus 1 over 1 minus z minus 1. I hope everybody can see that this expression is equivalent to what we have there at the beginning. So to organize this thing more, this expression more nicely, we can write minus 1 outside the brackets, and in the square brackets have 1 over 1 minus z minus 1 Now at this stage, we know that we have an expression of the sum of geometric series where we can take 1 to our initial term and the z minus 0 to be our common ratio. And we know that this will always develop to a0 plus a0 times r plus a0 times r squared, and so on. So coming to this point here, we have a minus 1 as a common factor, expanding in brackets there, we put 1 plus z minus 1 plus z minus 1 squared. I'm not mentioning here 1 times that because it's clear that the initial term is 1, so multiplying this is always going to be 1 is the identity for multiplication, we're going to have that. So plus z minus 1 times the additional term, which is 1 times 3 plus continues that way. Now expanding this, simplifying this by removing the brackets here, we've got minus 1 minus z minus 1 minus z minus 1 squared minus z minus 1 all cubed plus dash dash. So now we can see that we have got a similar series, though with different coefficients, but with the center translated to minus 1. And there we can add the condition that which were given there. Always please include the condition with your solution to state clearly under which conditions you are developing the series. So we've got that there. So geometrically, this means that this series is convergent within the circle of radius 1 centered at 1. So we can represent it this way. We have a series here. This we're going to call this, we're going to give this as our center 1, and then radius 1, which means this should be 2, and there we've got the origin. Then the series will be convergent within the circle, otherwise meaning that outside the circle, this will be the region of divergence of the series we obtained under the conditions given. So now I think that is enough. If you don't understand, please go through the explanation again slowly and make sure that you understand, especially the manipulations which are done in order to obtain this power series. Now, following for the next condition, we have the following condition. Now, if we look at this expression and what we saw before, here we've got series which are, the series which is a0 plus a0 times z to the power minus 1 plus a0 times z to the power minus 2, and so on. This is the kind of series we said is centered at infinity. And we know that absolute value of z equals to 2 is a circle centered at the origin. Now, when we consider absolute value of z less greater than 2, then that's when we can say now this region is a region of convergence set at infinity. Now, let's start with the function again. F of z equals to 1 over z minus z2, and we want this type of series centered at infinity. Now what we do again, our initial step will consider that condition, which is absolute value of z greater than 2, and we know that this is equals to, now because of what we have here, that the absolute z is always in the denominator, then this suggests that in this, under this condition, we can look at this condition being equivalent to 1 is greater than 2 over 1 is greater than the absolute value of 2 over z. So now, which means in this series, if we to obtain series like this where z is always in denominator, we would then need to have a term like this, which will more or less play the role of the common ratio of a geometric series. Now, to achieve this kind of expression in this expression as a sum of such a geometric series, this is what we do. Now, in our first step, we now start with our algebraic manipulation of the given function. Now we've got here z minus 2. To obtain this expression, we need to take out common factor z. So we've got common factor z here. And remember, when you're factorizing, you always divide. So now divide this z by z, you get 1. You divide 2 by z, you get minus 2 over z. Now reorganizing this, we can write this as 1 over z square brackets 1 over 1 minus 2 over z. Now having this one, we can see that we have got again the form of a sum of a geometric series where a0 is equals to 1 and our common ratio is equal to 2 over z. Now expanding this, what we write, you write 1 over z in brackets would repeat the development of a geometric series according to this, which would be initial term, which is 1, plus initial term times common ratio, which is 2 over z, plus initial term times common ratio, which is 2 over z squared, plus initial term times common ratio, which is 2 over z, in this case power 3, plus initial term times 2 over z all to the power 4, and so on. Then simplifying by removing the brackets and incorporating this 1 over z, we have 1 over z plus 2 over z squared plus 4 over z to the power 3 plus 8 over z to the power 4 plus 16 over z to the power 5 plus, if you check the pattern of development here, so there's a 2 power 4 z power 5, 2 power 3 z power 4, which you can say the general term here is going to be 2 to the power k over z to the power k plus 1, and that carries on to infinity. And then we can write the condition that this is for absolute value of z greater than 2, or otherwise meaning power series expansion which is set that at infinity. So again, you can see the manipulations here are very similar but differ depending on what condition you are given and what you should pull out as a common factor. Okay, so now we can also represent this thing, this type of region of convergence, just like we did before. You can look at this region. In that case now, region of convergence is outside the circle, but in this case, outside the circle centered at the origin. Let's say this one. In this case here, this region of convergence is outside this circle. That is if we were to draw the region of convergence. So I think up to this point, the example which were given at the beginning there has been fully discussed, and I hope the multiplications have been done, which we discussed here, have helped you to develop some ideas of how you tackle similar problems. For now, I would like to say thank you for listening.